evaluation of my data for the approximation are all of these Stroud points. If I've got a nonlinear problem, I'll have a pre-processing step where I do not the Decastel but some factorization to evaluate my current approximation, all of the quadrature points. That's order n to the d plus 1. That's why I wanted them at the quadrature points. So this could depend on you. So I start off with that. And then what I do is I change all of these indices from i's into alpha. So I sum over alpha 1. Well, the only difference between this and what I had before is that I'm multiplying by the quadrature weight. This is positive. These things are all positive. So that's a positive. These are all positive combinations. And I change the indices from I1 to ID into alpha 1 up to ID, and then I do that for all of these. And what I'm left with is something that is associated with the multi-indices or the domain points on the simplex. The result of the equation is that I've got these things, the multi-indices, they're nothing else than the components of my load vector. So I can use this sum factorization and the tensorial property or the pseudo-tensorial properties of Bernstein polynomials to evaluate the load vector for my finite element computation. So here's a claim, which I'm not going to prove. The number of operations needed to compute all of the moments, all of them, not just one, all of them, is order n to the d plus 1. So that's down from it. The naive algorithm with order n to the 2d, we're down to order n to the d plus 1. There is no existing basis that can do better than that. There are some bases that can do the same. So the point here is that I can obtain the element load vector at that cost, even with a variable data, and that includes nonlinear problems where I'm going to have to evaluate my current approximation as an iterative loop for solving a nonlinear problem. So I can deal with variable data, nonlinear problems, curvilinear elements, because curvilinear elements are just variable data again,